Today's topic is relative velocity. So here you are. You're on a train, and the train is going 9 meters per second. And this is you in the green shirt. And you're walking forward on the train at a velocity of 2 meters per second. So, to you, the velocity of the passenger relative to the train is 2 meters per second. The velocity of the train relative to the ground is 9 meters per second. So, to your friend who's watching you pull away on the train, it looks like you're going 11 meters per second because your velocity is being added to the train's velocity. So relative motion has to do with motion relative to the person that's observing the motion. So now you're not on a train anymore. Now you're on a boat. This is our next example. So if we have a boat here that has its engines off and it's just floating in the water, and the water is flowing downstream, then the boat just drifts downstream with the velocity of the water. In fact, we can take a look at that and call it the velocity of the water relative to the shore. Now, when you have the engines turned on and point the boat directly across stream, the velocity of the boat relative to the water is directly perpendicular to the direction of the water relative to the shore. So this is where we have to be careful because our velocity vectors are pointed in two different directions. So when we add these vectors together, we can't just do regular addition. What we have to do is vector addition. You remember vector addition, it's not so bad. So, when we're working with relative velocity, we have to be very careful in writing our subscripts so that they describe which velocity we're talking about. In this particular problem, the velocity of the water relative to the shore is 2 meters per second. And we'll call it VWS equals 2 meters per second east. Now the velocity of the boat relative to the water is 4 meters per second. We'll call it VBW equals 4 meters per second north. Alright, so now we have the pieces, but what we want to find is we want to find the velocity of the boat relative to the shore. And in order to find that, what we're going to have to do is we're just going to have to add these two vectors together. But since they don't point in the same direction, we're going to have to use our vector addition rules. Alright, so now that we have VBW and VWS, and we want to find VBS, let's write that out so it's a little bit more clear. We have the velocity of the boat with respect to the water plus the velocity of the water with respect to the shore. When we add those two vectors together, we get the velocity of the boat with respect to the shore. Now the important thing to notice here is these middle subscripts. The second subscript of the first vector is the same as the first subscript of the second vector, and they essentially cancel each other out, and what you end up with is a vector that has the first subscript of the first vector and the second subscript of the second vector. And that tells you that you're adding them in the right order. So what does this look like? Well, alright, so now we're just doing our vector addition. If we have the velocity of the boat with respect to the water of 4 meters per second north, and then the velocity of the water with respect to the shore of 2 meters per second east. When we add these two vectors together, our resultant vector starts where the first vector started, ends where the second vector ends, and this is the velocity of the boat with respect to the shore. And to find the magnitude, we just use the Pythagorean theorem. So it equals the square root of 4 squared plus 2 squared. So VBS equals approximately 4.5 meters per second.